problem solving exercises. Let me also share my screen. Okay. So, chapter 9 is what we'll be looking at today, starting today. And this is where we're going to deal with chemical bonding, right? That's basically the focus of this chapter. So, whenever we're talking about bonds in chemistry, we're basically talking about the attractive forces that exist between molecules or between atoms and molecules and ions, right? That's what holds them together, which prevents them from falling apart, right? So these forces are collectively called chemical bonds, right? And the very nature of these bonds, these forces, is that they are electrostatic forces. And what that means basically is that we have attractive forces between particles that are opposite the charge, right? So that is true, definitely true in the case of ionic bonding, which we're going to talk about later on, but it's also true when it comes to molecular bonding or covalent bonding. So let's take the simplest molecule, hydrogen, and look at the type of forces that are at play when we have two hydrogen atoms held together by a bond, right? So of course, each hydrogen atom is made up of a proton and a nucleus. And we all know that the proton is positively charged, and the nucleus has, I'm sorry, I misspoke. Protons and electrons, right? One proton, one electron. The protons are positively charged, the electrons are negatively charged, right? So when you have these collection of particles present within close proximity to each other, there are different forces that will come into play. You're going to have repulsive forces between like charges, right? So you're going to have repulsive forces between the two protons and the two electrons here. But you also will have attractive forces between particles of opposite charges, such as between the proton and electron here, this electron and this proton, and so on and so forth, right? So basically, the resulting stability of the system is as a result of the balance between those repulsive and attractive forces, right? And when it comes to the hydrogen atom, what you'll find is that the forces that would predominate is dependent on how close the protons are to each other. So what we are looking at here on the screen is a plot of energy on the y-axis and the distance between the two nuclei, all right, of the hydrogen molecule, okay? So if you're dealing with what's happening on the right side of this graph right here, right, to the extreme right, basically the energy will be zero, and that represents a situation where the two nuclei or the two atoms are far apart from each other to the extreme, right? So there's no force of attraction or repulsion that takes place. So therefore, that's what happens here. As you bring them closer, what happens is that the energy falls, and that's because of the attractive forces taking over as you go from this extreme until you get to this minimum right here. And the attractive forces will be between the protons in the nucleus and the electrons being shared between the two hydrogen atoms, right? So that continues until you get to this minimum. And then what happens as you start pushing the nuclei or pushing the two atoms close to each other is that the repulsive forces between the two nuclei starts to increase. So therefore, as a result of that, the energy will rise and continue to rise like this, right? And before, back in the day, scientists looked at this sort of interaction between two hydrogen atoms in a molecule and correlated to having two balls or two metal objects that are connected by a spring, right? So basically that's used as a model to somewhat explain what we observe here, which kind of makes sense if you think about it. If you have two round spheres connected by a spring, if you pull them far apart, so much energy is expended to break it, then basically there will be no attractive forces between the two spheres. If you bring them together more closely, then basically there will be repulsive forces, right? Which would cause the system energy to increase, right? So that's basically what is used very often to explain what is observed here, right? Now, it turns out that in the case of the hydrogen to hydrogen bond, the distance which represents the most stable state of the molecule is 74 picometers between the two nuclei. And you notice here that there's an energy value here of minus 436 kilojoules. So what that means is that in order to get the molecule from here to where the bond is completely broken, the amount of energy needed to break that bond would be 436 kilojoules, all right? So that's basically showing you the energy changes as you either increase or decrease the distance between the two nuclei. Okay, now let's talk about the Lewis theory of chemical bonding. G.N. Lewis, a very important chemist back in the day, he basically came up with some ideas and he came to the conclusion that when it comes to chemical bonding, it's the valence electrons that play a very fundamental role in bonding of both ionic and covalent compounds. So he continued his idea, expanded his idea to suggest that when you have a metal combining with a nonmetal, the valence electrons will be transferred from the metal to the nonmetallic atoms, giving rise to ionic bonding. So therefore, basically what he's saying here is that the metal will lose electrons from the valence shell, the metal ions resulting will be positively charged, the electrons will be transferred to the nonmetallic atom. As a result, that structure would be negatively charged, and therefore the attraction between the positively charged ions, which are the cations, and the negatively charged anions will be that ionic bond that holds the ionic compound together. All right. So that's what happens in the case of ionic bonding. Now, in the case of combination of two nonmetals, then basically you won't have the complete transfer of electrons from one atom to the other. Instead, what you'll have is a situation where electrons will be shared between the two atoms. And the result will be what's called the covalent bonds. Now, the attractive force that exists in the covalent bond or within a covalent bond is the attractive force between the nuclei of the separate atoms involved and the shared electron. And we're going to talk more about that later on. In any case, whether or not you're talking about ionic or covalent bonding, basically what is involved in both instances is losing, gaining, or sharing electrons to form the chemical bonds. And what tend to happen, not in all cases, but especially in the cases of the representative elements, what happens is that the resulting atoms, when they lose or gain electrons, form ions, which will have a noble gas configuration, right? So that's basically what Lewis came up with in terms of explaining the type of forces that exist between atoms or ions. Now, Lewis came up with this very simple notion of chemical symbols, right, or Lewis symbols. And it's very simple, nothing complicated about this. Basically, Lewis symbol for an atom is basically the chemical symbol of that atom, and then we put dots around it to indicate or represent valence electrons, all right? So just to give you some examples here, I think I have the list here. Right, so if you take the elements in period 2, starting with lithium, basically the symbol for, the Lewis symbol for lithium is the symbol for lithium, plus a dot to represent the only valence electrons, and basically you do the same thing for the others. Now, it says here that in writing Lewis symbols, what we typically do is put the 4 dots singly on each atom, and then if you have more electrons to add, then you pair them up. In my opinion, that's not really necessary, but you know, in some textbooks, that's what they do, right? Okay, so let's talk about answering this question. Give the Lewis symbols for magnesium, silicon, and phosphorus. This is very easy because all you have to do is write down the symbol of the element. In the case of magnesium, that would be Mg, and then you put 2 dots around it, and that's the Lewis symbol for magnesium. In the case of silicon, that would be this right here. And in the case of phosphorus, that would be this right here. And that's it, right? So that's basically how you write down the Lewis symbols for different elements. You write down the symbol for the element, and then you surround it with the dots, which represents the valence electrons, all right? Okay, nothing complicated about that. Okay, so let's talk about further the formation of ionic bonds and the consequences of that. So, as we said before, in the case of the formation of ions, you have atoms losing and gaining electrons, right? And therefore, the resulting ions will have a noble gas configuration. But you need to remember that even though the ions will have a noble gas configuration, we're not saying that they are actually noble gas elements, all right? Basically, what we're saying is that the electron distribution of the ions will be the same as the nearest group 8 element, right? So when you have the ions forming from a metal and non-metal, then basically, as I said before, there will be a strong attraction between the resulting ions because they are oppositely charged, and we call that an ampere, right? So the attractive force that exists between these ions, we call them ionic bonds, right? And then what results as a consequence of this is that you're going to end up with a very large collection of ions that would be in a very highly ordered arrangement. And we call this an ionic crystal. And I have a diagram on the next slide, which basically gives you the arrangement here. So this is basically representing the crystal structure of sodium chloride. The picture on the left is basically showing you what happens when you have a flask filled with chlorine and you add a small piece of sodium metal to it. You have a very explosive, very exothermic reaction that generates a lot of heat and light. And then once the reaction subsides and it cools down and you look at the bottom of the flask, you're going to see these crystals of sodium chloride, all right? And they basically exist as crystals because of the highly ordered arrangement of the sodium and chloride ions in what is called a crystal lattice. So this is the sodium atoms giving their electrons to the chlorine atoms. You end up with the sodium ions and the chloride ions, oppositely charged, attracted to each other, and then they assemble themselves into this arrangement as you can see here, right? And this is what is observed in ionic compounds. Now, the difference between different ionic compounds is that the repeat units within these structures might be arranged different, but what they all have in common is a continuous repeat unit throughout the whole growth structure of the ionic compound. And this should remind you that when it comes to ionic compounds, there's no such thing as a discrete unit, for example, of sodium chloride, right? Which means that there are no molecules, right? So it's not like water, for example, where you can identify a discrete unit made up of 2 hydrogen atoms and 1 oxygen atom. You cannot do that in the case of sodium chloride or any other ionic compound. They exist as seen here as a growth structure where you have repeat units and it's highly ordered, and that's the result, all right? Okay, so let me see what's next. Okay, so we can use Lewis symbols to show what happens in the case of ionic bonding. As I said before, the elements in the representative part of the periodic table. So I'm talking about elements in groups 1A all the way to 8A. These are the ones that are usually involved in, well, they're all involved in bonding for the most part, except in the group 8 elements. But in terms of making predictions as to how many electrons will be lost or gained, that can be seen in the representative elements, right? So again, using sodium chloride as an example, the sodium atom has only 1 valence electron, and that electrons will be transferred to the chlorine, which has 7 valence electrons. The result will be the formation of a sodium ion, which has now 8 valence electrons, and the chloride ion will also have 8 electrons as well in its valence shell. And as you can see, the sodium ion is positively charged, the chloride ion is negatively charged, and therefore there will be a strong attraction between those ions to form the ionic bond. All right. So let's apply this to this example right here. The question says, using Lewis symbols, you're to show the formation of ionic bonds between magnesium and nitrogen. What are the name and formula for the compound that results? Well, the last question can be easily answered based on our previous experience because if you have access to the tables that I've provided in Canvas, if you look up the formula for the magnesium ion, you see that it's what's going on? You see? Okay. You see that magnesium has a +2 charge, nitride has a -3 charge. So basically you're going to need 2 of these I'm sorry, you're gonna need 3 of these and 2 of these to form the magnesium nitride. So that's Mg 2 and 3. All right. So basically, you know that you're gonna need 2 magnesium atoms. And I'm going to draw the Lewis symbol for them. That's this. And then you're going to need 3 nitrogen atoms. Now, nitrogen is in group 5. So you know that there are 5 valence electrons for each nitrogen atom. Okay, I think I added an extra pair. This one here. All right. Why did I put Mg? Should have nitrogen. Okay, so this is nitrogen with 5 valence electrons. All right. So as I said before, the metal, in this case magnesium, will lose electrons to the nitrogen. Okay, so 1 electron will go here. 1 electron will go here. 1 electron will go here. Okay, I made another mistake. It should be 3 magnesiums. So, and 2 nitrogen. So, something was wrong. So let me erase this nitrogen here. Okay, so the actual formula should be Mg3 and 2. All right, so as I was saying, this electron will go here, and then this electron will go here, and this electron will go here. So the result will be going to have Mg2 plus, 3 of them. And you're going to have 3 nitride ions. Or 2 nitride ions, I'm sorry. And that's it. All right. So, oh, and by the way, it also asks for the name of the compound, and the name, of course, would be magnesium nitride. All right. And that's it. All right. So that's a relatively simple exercise. All right, so moving along. So let's talk about the energy changes that takes place when an ionic compound is formed from its respective elements, right? Now, what you're looking at here on the screen are different changes that will take place for sodium and chlorine atoms as they form gaseous ions, right? In the case of sodium, for it to form a gaseous ion, the amount of energy needed is 496 kilojoules per mole. And you should recognize that as the first ionization energy from the previous chapter. And then in the case of chlorine acquiring an electron to form the chloride ion, right, the energy change for that is minus 349 kilojoules per mole. And you should recognize that as the electron affinity for the chlorine atom, right? Now, based on the data that is provided here, it seems to suggest that the formation of sodium chloride is not energetically favored, primarily because the resulting enthalpy change will be positive. And usually, if the enthalpy change of a reaction is positive, that means that it's not energetically favored. That's not true in all cases, but true in, I would say, most cases, right? Now, another factor that we have to take into account is what is called the enthalpy of formation, which is the energy change that takes place when the elements in their ground state, well, not ground state, but their standard conditions to form the ionic compound as a result, right? And that seems to be more important than either the first ionization energy or the electron affinity, right? So two guys, one by the name of Bohr, the other by the name of Haber, came up with an approach which basically explained stepwise how you get from the original elements to the final product. So their approach is called the Bohr-Haber cycle, and I'm going to show you what that looks like for sodium chloride on this slide right here, right? So this here is the Bohr-Haber cycle for sodium chloride. So I'm going to explain how this works, all right? What I'm going to do is start from sodium and chlorine right here, okay? That's the start, okay? So you have sodium solid and chlorine gas, right? That's how basically they exist normally in nature under standard conditions, right? Now, by definition, going from the elements themselves to the final product, which is sodium chloride, that is called the enthalpy of formation. And in this case, for the case of sodium chloride, the enthalpy of formation is minus 411 kilojoules, right? So if you were to go directly from here to here, that's the enthalpy of formation, right? So the approach that is used by Bohr and Haber is where you're going to look at different changes occurring for the different atoms as you go from the start position right here until you get to the product, all right? So I'm going to go through each of these steps and show you what is happening. Now, the first step is where we go from sodium solid to sodium gas, all right? So we call that sublimation. I don't know if you have met that term before, but sublimation is where you go directly from the solid state to the gaseous state. So the enthalpy involved in that change, we call that the enthalpy of sublimation, all right? And in the case of sodium, that would be 107 kilojoules, all right? So that's what happens in the case of the first step, sublimation, going from sodium solid to sodium gas, right? The next step is where we go from chlorine gaseous molecules to chlorine atoms, right? And we call that, well, the energy required for that, we call that the bond dissociation energy. I'm just going to abbreviate that, that's BDE, right? The bond dissociation energy is the energy required to break up a bond between two atoms that are covalently bonded to each other. In the case of going from half Cl2 to Cl, the energy required is 122 kilojoules, right? So that's how we get to this stage here. Now at this stage, we have both sodium and chlorine gaseous atoms. So to go from here to here, what's happening is that the sodium gaseous atoms would be converted to sodium gaseous ions. In other words, you're removing an electron from the gaseous atom to form the gaseous ion. That would be the first ionization energy. First ionization energy. Ionization energy, all right? So that's the energy required to remove one electron from the gaseous atom to form the gaseous ion, right? And then the next step is where the chlorine acquires that electron to form the chloride ion. And this is be the electron affinity, all right, of the chlorine gaseous atom, all right? Now, before I continue, let me just say that you'll notice, or you should notice, that all the steps that we have looked at so far, sublimation, bond dissociation energy, and the first ionization energy, each of these steps are endothermic, right? So therefore, each of these values will be positive. On the other hand, the electron affinity where the chlorine gas gain, or chlorine gaseous atoms gain an electron to form the chloride ion, that is negative because that's exothermic, all right? So that's what happens as you go from Cl to Cl minus. Now the next step is where these two combine to form the sodium chloride. And it turns out that basically that's another exothermic process. And in this case, the enthalpy change involved would be equal to minus 787 kilojoules, all right? Now, let me just say something here, because this is, again, another situation where if you go to different sources, different textbooks, online sources, and so on, you see different definitions, right? Now, in some textbooks, they say that if you're going from the gaseous ions to the solid, that's called the lattice energy, right? Right, so by definition, the lattice energy is the energy required or the energy change that occurs when gaseous ions of opposite charges come together to form an ionic compound. In other textbooks, they define lattice energy as the reverse. In other words, the energy to break up an ionic compound to form the gaseous ions. And I checked your textbook, and your textbook says the lattice energy is the energy required to break up an ionic compound into its gaseous ions. So because that's what your textbook says, that's the definition I'm going to stick to, which means that the lattice energy in this case will be going from the sodium chloride solid to the sodium and chloride ions gaseous, which means that the lattice energy will be positive 787 kilojoule, right? According to the definition in your textbook, which is what I'm sticking. All right. So I just want to let you know that because, you know, if you wander off and look at some other textbooks, or if you go online, you might see the definition would be the opposite of what I just said. All right. But I'm sticking to the definition according to your textbook. All right. So basically, this is the Born-Haber cycle. And most of the questions that you're going to encounter when it comes to this cycle is for you to determine this right here, the lattice energy. The lattice energy is very important because the lattice energy is used as a measure of how stable the ionic compound is, right? The greater the lattice energy, the more stable will be the ionic compound. All right, so basically, what you're going to find is that, how should I do this? If you go from here, if you start here and you stop here, right? The energy change that would take place as you go from here to here would be the same as the energy change as you go from here to here, all right? So if I were to write down the mathematical relationship based on this, it would be plus 107 kilojoules plus 122 kilojoules plus 496 kilojoules plus minus 349 kilojoules. All right. And that total will be equal to minus 411 kilojoules plus 787 kilojoules. Right? So basically, if you add up all of this right here, that will be equal to all of this down here. All right. And as I said before, most questions will be asking you to determine this, which will be the lattice energy. All right. So that's basically what the Born-Haber cycle is all about. Okay. Any questions about this? Let's see. Oh, one person has decided to join us online. Oh, that's Miss Lee. Welcome, Miss Lee. Okay, so any questions? Any questions about this? Any questions? All right, so the next slide I think is an example that we can look at. Get this working. Okay, so here's an example. It says using the following data to determine the lattice energy. As I said before, most questions, that's what you're asking for. And it gives you the data. Enthalpy of sublimation of magnesium, the first and second ionization of magnesium, the bond dissociation energy of fluorine, the electron affinity of fluorine, and the enthalpy of formation of magnesium fluoride. So let's write down or draw a Born-Haber cycle for this. So what I'm going to do is start off with magnesium solid plus plus F2 gas. All right. So that's what we're going to start off with. So what I'm going to do now is start off with the magnesium. So to go from magnesium solid to magnesium gas, that would be the enthalpy of sublimation. And according to the question, that is equal to 146 kilojoules per mole. So I'm going to put 146 kilojoules per mole for the sublimation of magnesium. And then in the case of fluorine, it's to go from fluorine molecules to two fluorine gaseous atoms. The dissociation energy, the bond dissociation energy is 159 kilojoules per mole, all right? Okay, then we get to going from magnesium to magnesium 2+ gaseous ions. Now, because there are 2 electrons that you have to remove from the magnesium, that means that you have to basically add the first and second ionization energy to get the total energy required to remove those 2 electrons, right? So according to the question, where is it? They gave you the first ionization energy and the second one, right? So that will be the total of 738 plus 1451. So according to my calculation, I1 plus I2 will be equal to 2,189 kilojoules per mole. All right. Okay, and then now in the case of fluorine to be converted to 2 fluoride ions, the electron affinity, the electron affinity for 2 fluoride atoms would be 2 times the electron affinity for 1, right? So that will be 2 times, okay, what's the electron affinity? Minus 328 kilojoules per mole. All right. So, what I should have done earlier is this right here. Going directly from magnesium to fluorine to give you magnesium fluoride, solid, and the enthalpy of that would be the enthalpy of formation, which is minus 1124 kilojoules per mole. And then now, based on the definition in the textbook, as I said before, the lattice energy will be the energy needed to break up the magnesium fluoride into the gaseous ions. So that's what we're trying to find, right? That's what we're trying to find. Okay, so now that we have established the Bohr-Haber cycle for this compound, magnesium fluoride, we can write down the mathematical relationship. All we have to do now is saying that going from here to here, the energy required going from here to here is the same as going from here through magnesium fluoride to here, all right? So what does that mean? That means that, see if I can squeeze this down here. If you add this, this, and this, so that's 146 kilojoules per mole plus 159 kilojoules per mole plus 2189 kilojoules per mole. And then, I did not work out that part. So minus 328 times 2 is minus 656. Minus 656 kilojoules per mole. So that goes here, plus minus 656 kilojoules per mole. And all of that would be equal to the sum of the lattice energy, which is delta H lat, minus 1124 kilojoules per mole, right? So basically, I'm going to continue up here. The delta H lat will be equal to 1124 kilojoules per mole plus 146 kilojoules per mole plus 2189 kilojoules per mole minus 656 kilojoules per mole. And that's it. So let's see what that gives. 1124 plus 146 plus 2189 minus 656. And according to my calculation, this gives you 2803 kilojoules per mole. I have a sneaking suspicion that it's something wrong. Let me check something here. Oh, I missed that one. So I should add 159 to this here, kilojoules per mole. So let me add that plus Okay, so I got, 2962 as the final answer. So 2962, so that should be the final answer, right? Okay, so that's a typical Born-Haber cycle type of questions that you could get in your future exam, right? Okay, any question about this? Any questions? Any questions? Any questions? All right. Let me proceed to talk about Lewis structures, this time for molecules. So we talked about Lewis symbols, in which we use the symbol of the element and we use dots to represent the electron. We can extend this to represent molecules based on our understanding of how non-metallic elements come together to form a molecular compound, right? So the Lewis structure basically shows the combination of Lewis symbols that represents molecules, right? And basically you're going to have electrons being shared between atoms, and that will be represented in these Lewis structures. You'll also see what are known as lone pairs of electrons, which are not shared between atoms. We're going to get into that shortly. All right, so in most cases, not in all, but in most cases, what we find is that each atom in the Lewis structure for a molecule will have a noble gas configuration, where each atom will basically end up with either 8 electrons or 2 electrons on its outer shell. But as you're going to see later on, there are exceptions to that, especially when it comes to the larger elements within the representative region of the periodic table, right? So as stated here, the electrons can be shared, and as a result of sharing, you may have, or in most cases, you'll have atoms ending up with a noble gas configuration as a result. Now, it's important when it comes to Lewis structures, and also when it comes to some other topics that we're going to meet later on, it's important that you make a distinction in Lewis structures between what are called bonding pairs of electrons and what are called lone pairs, right? Now, in common practice, the bonding pair can be represented by a dash, or it can be represented by 2 dots, right? But keep in mind that if you're going to use a dash, that dash represents a pair of electrons being shared between the 2 atoms, all right? Now, you may have electron pairs which are not involved in bonding, and we call them non-bonding pairs or lone pairs of electrons. So just to give you a simple example, if you have 2 chlorine atoms coming together to form a molecule, right? You're going to have 2 electrons. These 2 electrons here will be shared between the 2 chlorine atoms, right? So we call that a bonding pair of electrons, right? All the other pairs of electrons that exist, we call them lone pairs or non-bonding pairs of electrons, all right? So this is one way of representing the Lewis structure, right? But we can also represent the Lewis structure using this, where instead of using 2 dots to represent electrons being shared between the 2 atoms, you use a dash or a line, and what you need to remember and understand that that dash represents a pair of electrons. Now, another way of representing this structure, which is my personal preference, is this right here. Right? So this line here represents a shared pair of electrons, and these lines here represents lone pairs of electrons, right? So you feel free to use any one of these in terms of drawing your Lewis structure. It doesn't matter to me. My personal preference is this one right here. I just find this easier to write down. All right? Okay. So let's continue. I have some examples here of different compounds and their Lewis structures. And just to, again, highlight the difference between bonding pairs and lone pairs. In this case here, we have the molecule methane represented here. And basically, you have carbon being bonded to 4 hydrogen atoms. And between the carbon and each hydrogen atom, there are 2 electrons or 1 electron pair that exists, right? So as you can see, this carbon atom has 8 electrons on its outer shell, and the hydrogen will have 2 electrons. In the case of nitrogen, there are 3 bonding pairs of electrons surrounding the nitrogen and a lone pair on the nitrogen atom. In the case of water, you have 2 bonding pairs and 2 lone pairs. In the case of hydrogen fluoride, you have one bonding pair here and two lone pairs on the fluorine, right? So that's just to highlight the difference between bonding pairs and lone pairs. Another thing I want to mention here, that's a point being made down here in this green box, right? And that is that whenever we're drawing Lewis structures, we are not concerned about the three-dimensional shapes, right? All we're concerned with is how the atoms are connected and where the bonding pairs and lone pairs are, right? So later on, we're going to be concerned with shapes, right? We're going to discuss that. But for now, we'll just be concerned with how the atoms are connected to each other and where the bonding pairs and lone pairs are, all right? So for example, in the case of water, you can write it like this, or you can write it in this arrangement. As far as Lewis structures go, they're both the same, all right? Because we're not concerned with, how the atoms are arranged in three dimensions. We're only concerned with how the atoms are connected to each other, all right? Okay, so let's talk about, before we get to some more Lewis structure examples, let's talk about the fact that we can have what we call multiple covalent bonds being formed. Now, basically in chemistry, if you have a pair of electrons being shared between two atoms, we call that a single bond, right? But you can have more than a pair, right? For example, you can have, in the case of carbon dioxide, 4 electrons being shared between the carbon and one oxygen atom on either side, all right? So basically, those 4 electrons would be 2 pairs, and therefore, we call that a double bond, all right? We can also have a triple bond where we have 3 pairs of electrons being shared between 2 atoms, as in the case of the nitrogen atom, all right? Or I should say the nitrogen molecule, all right? So for our level, that's a maximum, even though there are examples of quadruple bonds, right? But for all purposes, we won't get into that, right? We're only concerned with single, double, and triple bonds at this level, all right? So you need to understand that these bonds can also form, and later on, when we get into exercises of drawing Lewis structures, you're going to see how we go about forming those bonds, at least on paper. Okay, so that's multiple bonding, all right? Now, before we get to some exercises here, let's talk about the one example of the importance of experimental evidence. Now, based on the commonly drawn way of drawing the oxygen molecule, that suggests that the electrons are all paired, right? Including the non-bonding electron, right? Now, if you remember from the previous chapter, remember we said that there are certain magnetic properties that structures can display, right? And one of them would be diamagnetism, and another one would be paramagnetism, and then there's a third one, which is ferromagnetism, right? Diamagnetism would exist if there is a situation where all the electrons are paired, right? So based on the structure, you'd expect oxygen to be diamagnetic. But if you were to carry out an experiment to test this, what you'll find is that oxygen is not diamagnetic, it is paramagnetic, right? And that is demonstrated in this experiment right here, where liquid oxygen is poured between 2 poles of a magnet, and what happens is that the magnet attracts the oxygen, right? Which means that the oxygen in this form must have unpaired electrons, which means that it's paramagnetic. So what that means is that this structure here is not totally accurate in terms of representing what oxygen is in terms of its magnetic properties. More than likely, this will be the true representation of oxygen, where you have single electrons on the valence shell of each oxygen atom, all right? So that is more likely to be the arrangement in terms of the magnetic properties displayed by oxygen, all right? So basically, this highlights the fact that Lewis structures are useful when it comes to drawing the structures of molecules, but you need to keep in mind that there may be, as in the case of oxygen, instances where experimental results contradicts the Lewis structure that you would derive on paper, all right? Okay, so now we're going to get into how do we go about drawing the Lewis structure of molecules and also polyatomic ions. We're going to get into that as well. Okay, so basically, there are a couple of things that you have to keep in mind. One, the skeletal structure shows the arrangement of the atoms. If you have any hydrogen atoms present, then those hydrogen atoms will be terminal atoms. In other words, the hydrogen atom cannot be bonded to more than one atom, all right? And then also, in terms of determining which atom would be the central atom, it would be the atom that has the lowest electronegativity. And of course, you guys will have the tables to look at in order to determine which atom involved in a structure would have the lowest electronegativity. When it comes to oxyacids, right, you have to make sure that the hydrogen atoms involved are bonded to oxygen atoms, all right? And then you need to be sure or make sure that all molecules or polyatomic ions, they have compact symmetrical structure. So for example, just to give you a brief example, if you're asked to write down the Lewis structure of the sulfate ion, then it is more likely that the arrangement will be this, where you have the sulfur in the middle and the oxygen surrounding it, as opposed to sulfur here, and then you have two oxygens here, and then you have two oxygens here, right? This is more than likely not going to be correct. You're more likely to have this arrangement in the case of sulfate. You want it to be compact, where you have the central atom, which will be the least electronegative atom, and then you surround it with the other atom, all right? Okay, so with that said, let's get into the steps involved, right? How do you go about drawing the Lewis structures? Let's say you're given the molecular formula, or you're given the polyatomic ion formula. How do you go about drawing the Lewis structure of that particular structure? The first step is you need to determine the total number of valence electrons. And that's very easy because all you have to do is consult the periodic table for the group, for the representative elements. The group numbers would be the number of valence electrons, right? And then you add them up, and that gives you the total number of valence electrons. So that's the first step. The second step is that you draw a plausible skeletal structure and you connect the atoms by single dashes or single bonds, covalent bonds, all right? The third step is that you place pairs of electrons as lone pairs around the terminal atoms to give each terminal atom an octet, with the exception of hydrogen, because of course hydrogen cannot have an octet, it will have a duet, which will be satisfied already if it's bonded to another atom. And then the fourth step is that if you have any extra electrons left over, you place those electrons on the central atom as lone pairs, all right? And then the fifth step, if necessary, and if there are not enough electrons, you're going to move one or more lone pairs of electrons from the terminal atom to form multiple bonds to the central atom, all right? So these are basically the steps involved in drawing Lewis structures. And the best way to learn how to use them is to go directly into some examples. So let's look at this first example here. This question says, write the Lewis structure of nitrogen fluoride. So I'm going to show you stepwise how to go about doing that. So I'm going to need some space. So let me open this up here. So LF3 is what you're given. NF3. All right. So the first step, if you recall from the list I just showed you, is that you're going to add up the total number of valence electrons, right? So you go to the periodic table and you look up the group numbers for the different elements. In the case of nitrogen, that would be 5 because it's in group 5. And in the case of fluorine, that will be 7. But because you have 3 of them, you have to multiply that by 3. So that gives you a total of 21, right? So you add 21 to 5, and that gives you 26 electrons. And that would be equal to 13 pairs. Now, personally speaking, I like to express the number of electrons in terms of pairs. You're going to see why, all right? So, after we have determined the total number of valence electrons, then we start putting an arrangement of the atoms. The less electronegative atom would be placed in the middle, which is which is nitrogen, and then we surround it with the fluorines. And again, we are not concerned with the three-dimensional arrangement, so it doesn't matter how you place them around the nitrogen. So you can do it like this, and that is sufficient, right? So the next step is that we assign the bonding pairs first, right? Now we have 13 pairs of electrons to assign, right? So we start assigning the bonding pairs. 1, 2, 3, right? So we have used up 3 of the 13 bonding pairs, right? And we have some pairs left over. And according to the list of rules that we just looked at, we start adding pairs to the atoms around the nitrogen, making sure that each atom ends up with an octet, right? So we added 3 here for bonding pairs. The 4th pair would go here. So that's 4, 5, 6. So that has its octet. Then 7, 8, 9, 10, 11, 12, right? So now we have assigned 12 electron pairs. We have 1 pair left over because remember we have a total of 13. So the question is, where will that extra pair end up? And that is right here. That would be the Lewis structure for nitrogen difluoride. All right? Any question about this? Any question? And please note, in this particular structure, all the atoms each have 8 electrons on its outer shell, right? If you look at the fluorine here, you have 2, 4, 6, 8. Same is true for that fluorine, same is true for that fluorine. And in the case of nitrogen, you have 2, 4, 6, 8, right? So each atom ends up with 8 electrons on its outer shell. All right. Okay, any question about this? Any questions? Any questions? All right, so what was the next structure? SCl2. So we're going to do the same thing as we did for NF3. So let me get rid of all this. Okay, so SL2, sulfur dichloride, is the next molecule, all right? So we're going to go through the same steps as before. We consult the periodic table to look up the group numbers for the different elements. In the case of sulfur, that would be 6. In the case of chlorine, that would be 7. But because you have 2 of them, we multiply that by 2, so that would be 14, contributed by chlorine. So when you add 6 to 14, that's 20 electrons, which will be equal to 10 pairs. All right? And then we put the sulfur in the middle and surround it with the chlorines. Again, it doesn't matter how you put the chlorines, right? And then we start with the bonding pairs. Now remember, we have 10 pairs to assign. The first 2 will go here, and then 3, 4, 5, 6, 7, 8. We have 2 more pairs to assign. Those 2 pairs will go here and here. And that's it. And that would be the Lewis structure for sulfur dichloride. And again, you'll notice that in this structure, each atom has an octet. All right? Okay, any question about this one? Any questions? Okay, what's the next example? Okay, what's going on here? Okay, silicon tetrachloride. So let me go back here. Let me delete this. All right, so SiCl4 is the next one. So let me hear what you have to say, because now you should be able to tell me how we go about doing this based on the previous 2 examples. So what's the first step? You mean the valence, the group numbers, right? So silicon will contribute how many valence electrons? 4. And each chlorine will contribute how many? 7. But there are 4 of them, right? So that would be 28. So 28 plus 4 gives you 32 electrons, which will be equal to 16 pairs, right? What's the next step? What's the next step?
Write out the structure, so silicon in the middle and then the chlorines all around.
Okay. And then what?
Your bonding pairs first.
Okay, so remember now, we have 16 to assign, right? So
Yeah.
1, 2, 3, 4, right? Then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and that would be the Lewis structure for silicon tetrachloride. All right? Any questions about this one? Any questions? Any questions? Okay, now things are gonna get, unfortunately, a bit more complicated. Let's talk about, before we get to the more complicated situation, let's talk about this concept of formal charge, right? This will become important because later on we're going to see how multiple bonding can form within a molecule based on this concept. So here's a definition of formal charge. Formal charge is a difference between the number of valence electrons in a free atom and the number of electrons assigned to that structure when bonded to other atoms in a Lewis structure. Please note that a formal charge is basically a hypothetical quantity, which is a useful tool for determining the Lewis structure, especially when it comes to multiple bonding. Now, there's a formula that I use to calculate the formal charge, but before we get to that, some other things about formal charges that you need to keep in mind when drawing Lewis structures. Usually, the most plausible Lewis structure is the one with no formal charges, right? So we try to work with a situation where there are no formal charges, even though that's not always possible. The next thing here mentioned is that when formal charges are required, they should be as small as possible. And when it comes to negative formal charges, those charges must appear on electronegative atoms. And also, adjacent atoms in a structure should not carry formal charges of the same sign. All right, so with that said, let me give you the formula for calculating the formal charge. So you're going to see this expressed in different ways in different textbooks. This is the formula that I prefer to use. So it is the formal, I hate writing. The formal charge of an atom is equal to the group number of the atom minus half the number of bonding electrons minus the number of non-bonding electrons. All right, so half the number of bonding electrons here and the number of non-bonding electrons there, right? So this is the formula that I use to calculate the formal charge of any atom. And I think in your textbook it's worded differently. You can use that formula as well. I have no problem with that, as long as the result is still the same, right? So whenever you're determining the Lewis structure of any molecule or any polyatomic ion, this has to be a part of that process, right? Now, I did not use this calculation in the previous example because I knew that the formal charges in all those cases for all the atoms involved would be zero. But just to illustrate how we use it for the last example. So let me go back to this right here. So this is what we got in the final answer. So if I were to calculate the formal charge of silicon, right? Based on the formula, let me write down the formula here to remind you. So formal charge is equal to the group number minus half the number of bonding electrons minus the number of non-bonding electrons. That's the formula we're using, right? So that's the formula. All right. So for the silicon, the group number is 4, right? Minus half the number of bonding electrons. So if you look at the silicon atom, you have 2, 4, 6, 8. So that will be half of 8, right? And then the number of non-bonding electrons for the silicon is 0, right? So when you work this out, what do you get? 4 minus half of 8, which is 4, which is 0. So the silicon atom has no charge, right? And then if you carry the same calculation on the chlorine, right? Using the same formula, the group number is 7 minus half the number of bonding electrons. Now, please note, we are carrying out the calculation of one of these chlorines because all these chlorine atoms have the same electronic arrangement, right? So if you carry out the calculation on one, it's the same for the other, right? So if we focus on this chlorine here, right? What's the number of bonding electrons? And that would be 2. So half of 2 minus the number of non-bonding electrons, which would be 2, 4, 6, right? So that would be 7 minus half of 2, which would be 6 minus 6, 0. So therefore, there are no formal charges present within this molecule, which means that the molecule overall will have no charge, right? So please note that whenever you're doing, or if you're asked to determine the Lewis structure of anything, you need to include as a part of the process the calculation of the formal charge for reasons which we're going to see shortly. Okay, so let's go back to the PowerPoint here. And this is just some other example. Oh, you have a question? No. Oh, okay, sorry. All right. So these are just some other examples of formal charges here. Okay, so now we're going to get into the reason why we need to determine the formal charges by looking at these examples. So the first example is COCl2. So let me get out of this here. And let me delete. Okay. Okay, so the formula is COCl2, all right? So the first step is the same as what we've done before. We go to the periodic table, we look up the group numbers for carbon, which is 4, oxygen, which is 6, chlorine, which is 7, but we have to multiply that by 2, so that's a total of 14, and then we add them up to get a grand total of 24 electrons, which will be equal to 12 pairs, all right? Then we put the carbon in the middle, and we surround it with the oxygen and the 2 chlorines. And again, it doesn't matter how you place them, because we're not concerned with the shape at this juncture. And then, as before, we start off with the bonding pairs, 1, 2, 3, then the non-bonding pairs, which would be 4, 5, 6, 7, 8, 9, 10, 11, 12, all right? Now, this is where you have to, at this stage, you have to calculate the formal charges of each of the atoms, right? So I'm going to start off with calculating the formal charge of oxygen, right? So based on the formula, let me write down the formula again, just to remind you, formal charge is group number minus half the number of bonding electrons minus the number of non-bonding electrons, all right? So that's the formula that we're going to use, all right? So in the case of oxygen, the group number of oxygen is 6, right? Minus half the number of bonding electrons. We have only one bonding pair here, so that will be half of 2, right? And then for the non-bonding pairs, it's 2, 4, 6. All right. So when we do this calculation, this works out to be equal to -1. So what that indicates is that there's a -1 charge on the oxygen. All right. Do a similar calculation for the chlorine, right? So in this case here, we'll just do one calculation for each chlorine atom. It's the same calculation, so we're killing 2 birds with 1 stone. So using this formula, group number is 7 minus half the number of bonding electrons, which for chlorine, for each chlorine that's 2, minus the number of non-bonding electrons, which would be 2, 4, 6, and that works out to be 0. Right, because 7 minus half of 2, that's 6, minus 6 gives you 0. So this chlorine and this chlorine has no charge, right? Then we get to the carbon, formal charge of carbon, right? So in this case here, the group number is 4, minus the total number of bonding electrons, which would be 2, 4, 6. So that's half of 6, minus the number of non-bonding electrons, which would be 0. So that would be 4 minus 3. That's +1. So the carbon here will have a +1 formal charge on it. Now, when you have a situation like this, where you have one atom which has a negative charge bonded to another atom which has a plus charge, what will happen is, in this case, the pair of electrons here from the oxygen will move down here to form an extra bond. The result of that is that this negative charge will cancel out this plus charge. So the final answer in this case would be Cl, C, double bond O, and then we have the 2 lone pairs on the oxygen, and then single bond Cl, and then the 3 lone pairs on the chlorine. And this, folks, will be the final answer. All right? So you see the reason why we have to calculate the formal charges, right? Because by calculating the formal charges, then we can see where the charges are. If you have two atoms with opposite charges, then there exists the possibility of multiple bonding occurring so that you can get your final structure. Okay, any question about this? Any question about this example? Any questions? Any questions? Okay, so let's move on to the other example, which is sulfur dioxide. So we go back to this right here and delete all of this right here. Okay, so what was the compound again? SO2. Okay, so sulfur dioxide, right? So first step would be what? What's the first step? So, excuse me. Sulfur would contribute how many?
6,
6. Oxygen would contribute how many?
6,
6 times
2,
2. So that's 12. So that gives a grand total of 18 electrons, which will be equal to 9 pairs. Right? So we put the sulfur in the middle and surround it with the oxygens. And then we put the bonding pairs first. We have 9 pairs to play with. So 1, 2, then 3, 4, 5, 6, 7, 8, and then 9. All right. Then we calculate the formal charges. So what's the formal charge for oxygen? What's the formal charge for each oxygen? Same calculation for each of them. How would you calculate the formal charge of each oxygen? Let me remind you of the formula. Formal charge is equal to group number minus half the number of bonding electrons minus the number of non-bonding electrons. So in the case of oxygen, what's the group number? 6 minus half the number of bonding electrons. What's the number of bonding electrons for each oxygen? Hmm?
6,
No.
that's 3,
Look at the structure.
1, 2,
2, exactly. And then what's the number of non-bonding electrons for each oxygen? That's 6. So this works out to be -1. So what that means is that each oxygen here has a -1 charge. So let's do the same calculation for sulfur. So what's the group number of sulfur? 6 minus half the number of bonding electrons. So what's the number of bonding electrons for the sulfur? 4 minus the number of non-bonding electron, which is 2. So that's 6 minus half of 4. So that's 6 minus 2 minus 2. So that gives you +2. So the sulfur here has a +2 charge, right? So again, we have a situation, in this case, we have a situation where we have two negatively charged oxygen atoms bonded to the central atom, which has a +2 charge. So what's going to happen? This pair of electrons will go here. And when that happens, this negative charge will cancel one of the 2 plus charges. And then this pair of electrons will go here. And that means that this negative charge will cancel out the other plus charge. So the final answer is going to be and that's it. That will be the Lewis structure of sulfur dioxide. All right. Any questions? What time is it, by the way? Ooh, almost done. All right. So that's basically how that is done. Any question about this? Any question? All right. We're going to stop here today. But before you leave, okay, we're going to get to this example. You can try this example on your own if you want to, but we're going to get to that example and then look at some problems and questions. Okay, so I think I posted an announcement about your next test, right? So just to remind you, that test will be on November 25th, which will be next week this time. All right? And that test will be based on chapter 6, 7, and 8. And I believe I sent you your graded, those graded assignments, 6, 7, and 8. And I think I've also posted in Canvas the answer key for those assignments. And Ms. Putz showed that I published a test, a past test, which is based on those assignments. So you can use that to help you to review as well. All right. So chapter 9 that we're in the middle of will not be on that test. All right. And I think that is it. Unless there are any questions, that's all I have to say by way of announcement. All right. So with that said, I will see you guys on Thursday. Well, Wednesday, guys. I'll see you with that. All righty then.
Did you wanna pick a date for when I have to pick my date?
All right, when do you want, I mean, you want to do it before or before the 25th or after?
So our final is the 11th of December.
I don't remember that, I think that sounds right, yeah, but I have to check to make sure.
I'm taking my math on Monday morning. So I don't wanna take the same day, so, I can take it. Are we having class on Tuesday?
We have in class on,
Tuesday is the exam.
well, no, Tuesday will be the test, next Tuesday. And the rest of the week will be the holiday.
Oh, no, I was talking about the final, not our chapter 3 test.
If I remember correctly, again, I have to confirm it, but if I remember correctly, it's on, let me see if I can find this quick. So,
That's in material.
what's that?
This was a T.
Hmm?
No, that's why I rescheduled, I think my list came out
Oh,
on that Thursday, so I had to take all my exams early.
yes, I've been there.
At least it's not doing so weird though.
Yeah, Leila is also accompanied, she gotta get those removed soon.
Yeah, I've been there.
Surprisingly,
I think I was probably about your age when it happened to me.
Gotcha.
Remember, I was in college, I remember.
Like, has that happened yet? Yeah,
Yeah, that's when the
Yeah.
tooth started breaking up from underneath
Yeah, take care of it before it hurts.
what he said.
Yeah, it's not,
Okay, I can't take it a long time to load up, but
it's all good.
yeah, it's all about right. What I'll do is, I might be able to confirm it when we're in, and then we can talk about that.
Okay.
Yeah.
That's okay. That's it.
oh, I was here, I was late.
Oh, what's the last name? Oh, I got it. Yeah. Okay, Miss Lee, I'm leaving now. So I'll see you in lab, hopefully.